Exam 2 review. So here we're just going to go through a few problems that I think should be helpful for studying for the exam. And let's get into it. Problem number 1. So here it gives us a circle, and it wants us to find the length of the arc. So on my own screen, I've drawn the arc here is S. It's this bolded line. And then find the area of the sector subtended by the angle. So all that means is it means what is this area in here, right? So what is the area of that little piece of the circle? And so to do both of these, it's not unreasonable at all. And the sector isn't even too bad. So if we go through, what do we know? So here I already have it circled. But the 9 pi over 20, that is the angle measure in radians. Well, what is 1 radian? 1 radian is the angle measure that if you were walking along the outside of the circle, you would move 1 radius. So then if I know what the radius is, I can figure out how long this angle is. S would be equal to, well, how many radians is it? 9 pi over 20, number of radians. So that's our angle theta, times the radius. So here the radius is 4. So I have 9 pi over 20 times 4. And now I would put this into a calculator, and I would get that this is roughly 5.64. And then my unit there is in feet, because the radius is in feet, and that's a length. So we have 5.64 feet, roughly. And this is the formula in general. Although trying to memorize it by a formula might be dangerous, just because there's a lot of things that could be running around in your brain. It's easier to cross wires. To find arc lengths like this, I prefer just thinking about it as it's literally just your angle measure in radians. How many radians do you have to go? Well, that tells you how many radii you have to move. So just multiply those two numbers together. The area is a little different. So here it wants the area of this sector. It wants the area of like this region. So how do we find that? Well, the area of a normal circle is A equals pi r squared. And so if you want a sector, there's a little bit of a weird thing that happens. It's almost theta times r squared, except you need a little 1/2. And that's because theta can get as big as 2 pi. So you need to cancel out that 2 is where that 1/2 comes from. Here maybe a formula would be a little bit better, but it still should look like the formula for a circle. It still has that r squared on it. But now you just take half of whatever your radius is, or whatever your angle measure is. Very importantly, it has to be in radians. Okay, so here though, same story. 1/2 times 9 pi over 20 times here our radius is 4 squared. And we could do some simplifying here, but we're going to have to put it in a calculator and simplify anyway. So there's no real reason to simplify if I'm going to make the calculator do all the work to begin with. And we're putting that in the calculator right now. And we get that this is roughly equal to 11.31. And now because it's an area, its unit is feet squared, or square feet. So both of these formulas, I think, are helpful when you're trying to find the arc length. I personally think it's easier to remember it as just how many radians are you walking through? Well, that tells you how many radius you have to walk around the circle. So just multiply those two numbers. But there's the formula there if you want it. And then for area of a sector, it's a little tricky. It's almost theta r squared, except theta could be as big as 2 pi, so you have to divide it by 2. And so those are your formulas, and that's how you figure out a problem like that. Problem number 2. use the image below again. So we've got our same circle as last time, except now the numbers are a little bit different. But the other thing that's different, the thing that we need to be careful of is our angle measure is in degrees now, not radians. So for our dias from the last problem to work, we need that angle measure to be in radians because that tells us how many radiuses are we walking through. And so if we go to the problem that I've written down here, if we want to find S again, then we cannot multiply 130 and 11 because 130 degrees doesn't mean anything in terms of how many radius do I need to walk through? How far do I have to go? So for that to make sense, for these formulas, if you're using those to make sense, your angle measure absolutely, positively has to be in radian form. So if I want to convert from degrees to radians, well, pi radians is half a rotation. 180 degrees is half a rotation. And so then this angle measure in radians is 13 pi over 18. So we have 13 pi over 18. And now we can proceed exactly like we did before. If this red line here is S, then S is just equal to our angle measure in radians over 18. Again, I want to really double down. For these to work, this has to be in radians. And then our radius is 11. We put that in a calculator, and we get roughly 24.96, and here our units are inches. We always want to remember the units. That's just good form, because then you don't ever have to worry about ambiguity or people being uncertain. So 24.96 inches. And then now we move on to the area. Area is, and I always remember it's almost the angle times r squared, except that's too big. You need to cut it in half. And my reasoning behind that is always because theta could be up to 2 pi, you'd get twice as much area if you didn't have that 1/2 there. So we plug that in. Again, though, theta absolutely has to be in radian form. If it's in degrees, it's going to give you the wrong answer. Times 11 squared. All right, and same story as last time. Just put this in the calculator. So that's what I'm working on right now. And what we get is 137.27, and then we have to be sure that our units are inches squared. This is an area of something, so its units are going to be a square. And so that's how you do problems like these. You might have to convert degrees to radians, but beyond that, it mostly comes down to find arc length, multiply your radius by your angle measure in radians. To find area, it's almost pi r squared, but instead of pi, you replace it with your angle divided by 2. Here's a plain and simple, just evaluate all of these trigonometric functions. And while we're here, let's go ahead and rationalize any denominators, just so we're making sure we're not out of practice on that. So I've written them down here. Sine, cosine, tangent, these match the document. And so I've brought with me a unit circle. And how do we figure out the trig functions? Sine and cosine, if you have the unit circle, should be easy, because all you have to do is go to the angle. So sine, for example, is pi over 3. So here's pi over 3. And then what I do is I just take the y value that goes with that. So here my y value is square root of 3 over 2. And so that's my answer here, square root of 3 over 2. Do note the exam will ask you for exact answers. And so what that means is if you put this in your calculator and you get like 0.71 something, you're not going to get credit because that's not an exact answer. We need to see that you can get it off the unit circle and that you know what these things mean. And that's important because if you go on to say physics classes, engineering classes, very often you're breaking things up into their x and y values, and that corresponds with cosine and sine. Right triangles come up a lot, and these things just show up all the time. So knowing what sine and cosine really are very important. Anyway, so cosine of minus 3 pi over 4. So let's move on to this next one. And so there's a few ways to do this. One is you can add 2 pi to minus 3 pi over 4. So you can think about it that way. This isn't on the unit circle. I could say minus 3 pi over 4, add 2 pi. That will give you, if you simplify that, you get 5 pi over 4. You have to get a common denominator for that. And so 2 pi would become 8 pi over 4. Minus 3 plus 8 is 5. The other way, the way that I personally think about it is I move down 1 pi over 4. That puts me here because minus says move down, not up. Move minus pi over 4. Move minus pi over 2. That's a second pi over 4. And then move a third one. And so here we take the x value. We get minus root 2 over 2. Okay, so minus root 2 over 2. Next, tangent of 5 pi over 6. So how do we do tangent? Well, let's go to 5 pi over 6 first. And we remember that tangent is sine divided by cosine. So there's sine over cosine. We've written it in that form. And now using the circle, we get sine of 5 pi over 6 is the y value, is a half. So we get 1/2 divided by cosine at that value is minus root 3 over 2. I get 1/2 times 2 over minus root 3. The 2's cancel, and I'm left with minus 1 over square root of 3. If I didn't have to rationalize denominators, that would be my final answer. That would be good enough. But here, because I need to rationalize, I'm going to multiply by the denominator over itself. So I'm going to multiply by square root of 3 over square root of 3. And I pick this number because that's what's in the denominator right there. Put everything together, and I get square root of 3 over 3. So let's write that, not in red, root 3 over 3. And that's our final answer. Has a nice rational denominator in case we ever need to like add it to a whole bunch of other stuff. That's the reason why you might want rational denominators, is because you might need to get a common denominator to begin with. Okay, so now 2 more. Cotangent of 3 pi over 2. So then the idea is similar. We go to 3 pi over 2 down here. Cotangent, we have to remember, is cosine. I know this is probably behind the picture, but I'm going to move it in just a second. So cotangent is cosine of 3 pi over 2. Of sine of 3 pi over 2. Oh, no, you can see it the whole time. And then cosine of 3 pi over 2 is 0. Oops, that wasn't meant to be so big. So here we get 0 on top. On the bottom, we get minus 1. Well, if I divide 0 by anything, we just get 0. If we add tangent of 3 pi over 2, it's possible you could get 0 on the bottom. If that ever happens, you would want to write undefined. But 0 on the top is perfectly okay. If I take 0 and divide it by a number, I just get a number. One more. Secant of 7 pi over 4. Secant is 1 over cosine 7 pi over 4. So now we go take a peep at 7 pi over 4. Here it is. Cosine is square root of 2 over 2. So this is 1 over the square root of 2 divided by 2 is 1 times 2 divided by the square root of 2. And so there's two ways to think about this. The easy way, or maybe not the easy way, the slick way, is I'm taking a number and I'm dividing it by its square root. So then I just should get the square root. In the same way, if I divide 9 by 3, I just get 3. But if you want to see a better or the more grueling way to do that, so this is the way that would always work. It's not so slick. Is I say, okay, rationalize the denominator just like we did before. So just like we did with 1 over root 3. Do that same thing here. You get 2 square root 2 over 2. But then the 2's cancel. So the way I showed you above, that still works for this. This is a little bit slicker. If you divide any number by its square root, then you just get the square root of that number. Okay, and that's finding all the trig values. Problem 4. If sine of t is 2 over 7 and t is in quadrant 1, find basically all the other 5 trig functions. And here it has a little bit of mercy on us. It says you don't need to rationalize any denominators. So let's set up our, here's a classic little chart here. This is just to keep things organized. As long as I can tell where everything is, it won't be a problem. But this is how I make sure things are organized. Cotangent t. And then we have secant, cosecant. So there's all 6 of our trig functions. Now we just have to find them. We were given one. We were given sine is 2 over 7. And we also know t is in quadrant 1. Okay. So that's the information we want to roll with. And so the way you want to do problems like this, when you're asked to find all 6 trig functions, is you're given usually anything but tangent or cotangent. So first make sure you have sine or cosine. We'll see in the next problem, maybe you don't start with it, but you can get it pretty quickly. But here we were just straight up given sine. And so using that, the next thing you want to do is find cosine. Once you have sine and cosine, the other 6 are really quick and easy to find. Well, not easy, but they're a lot easier than cosine. And so what's the formula that's going to get you through the day? The big thing you need to use is sine squared of t plus cosine squared of t equals what? That's going to be what gets us through. That's what's going to help us figure out what we need. And so here I know what sine is. So that tells me 2/7 squared plus cosine squared is 1. 2/7 squared, that's 4 over 49. Plus cosine squared of t is, that should be a 40, not a 50. 4 over 49 plus cosine squared equals 1. So now I subtract 4 over 49 from both sides. So we get cosine squared is 1 minus 4 over 49. If you're not comfortable subtracting fractions, then we want to get a common denominator. So 1 is 49 over 49 minus 4 over 49 gives us 45 over 49. So that's cosine squared. Actually, let's just keep going here. So cosine squared of t is 45 over 49. But that's the square. So let's take a square root of both sides. So square root, square root. Then cosine of t is, we need a plus or minus to start. Plus or minus. And now when I'm square rooting a fraction, I can turn it into two different square roots. So if I have the square root of a divided by b, then that's just the square root of the top divided by the square root of the bottom. Now this simplifies to be the square root of 45 divided by 7. And here we could also simplify this radical if we wanted, but the instructions didn't say to worry about that, so we're going to go ahead and leave it as 45. And so we did all that work to say cosine of t is the square root of 45 over 7. And so even though we only have 2 of 6, we're actually well over halfway done, because now everybody else just uses sine and cosine. So tangent equals sine over cosine is 2 over 7 divided by root 45 over 7 is 2 over root 45. And you can think about how we got that a few different ways. The way that always works is to just multiply by the reciprocal, but then you'll happen to see that the 7's cancel out. Or if I'm dividing the top and bottom by 7, then I'm really not doing anything. So I get 2 over the square root of 45. Once I have that, then the easier way to find cotangent is to just flip tangent. And so here you could literally just at this point in the problem, if you wrote this, if you showed me where you got tangent, I'd be fine with you flipping it. Perfectly fine by me. And then secant and cosine do the same thing. So here I'm just writing out the work for why that happened. But then we flip by that bottom fraction, we get root 45 over 2. Secant is cosine flipped. It's 1 over cosine t is 1 over square root of 45 over 7. But if you have 1 over a fraction, then you can just flip it. So this is now 7 over root 45. And then for cosecant, you do something similar with sine. We're going to get 7 over 2. And the reason for that is because cosecant of t is 1 over sine of t is 1 over 2/7. And so I would just flip that fraction that's down there in the bottom. And that's how I get that. Problem 5 is similar. So it tells us what secant of t is, 13 over 12, and tells us t is in quadrant 4. So let's add that. We're in quadrant 4. Now find, and it basically just says the other 5 trig functions. And same story as last time. No need to rationalize any denominators. We're just going to let calculators take care of everything. And so it told us secant, I want to make sure it was secant, is 13 over 12. Yep. So secant is 13 over 12. And now we need to find the other 5 trig functions from that. And so this is like almost beat for beat the same problem as last time. The only thing is secant of t is what we have. We want cosine of t. And so that means 1 over cosine of t is 13 over 12. But if we cross multiply and divide, we would get cosine of t is 12 over 13. So that's kind of the biggest wrinkle that a problem like that could have, is I could give you secant or cosecant first. You have to flip it to find sine or cosine. But after that, it turns into the exact same problem as last time. We're going to go through the exact same steps. I'm going to use my equation sine squared of t plus cosine squared of t is equal to 1. This time I know what cosine is. So sine squared of t plus 12/13 squared equals 1. Go down one more level. 144 over 169 is equal to 1, plus the sine squared over there, sine squared plus that. So now, sine squared of t is, I'm going to prep this one to get ready to subtract. You can always do this, it'll work for these types of problems. 169 over 144. I get sine squared of t is 25 over 169. Now we take a square root. So now, sine of t is plus or minus again, square root of 25, square root of 169, plus or minus, hey, those are both perfect squares, 5 over 13. So actually no rationalizing necessary. But now how do we decide whether it's positive or negative? Well, we're in quadrant 4. That's this bottom one here, bottom right. And so there the y values are negative. And since the y values are negative there, that means sine is negative there. So then sine of t is equal to 5 over 13. Okay, so now we have sine. Sorry, it's negative that, because it's in the bottom. It's negative 5 over 13. This is why you go back and you give your exam a once-over if you have time, just to make sure everything looks okay. So now we have negative 5 over 13. And now that we have sine and cosine, the rest goes quick, especially because we already have secant anyway. So now tangent is sine over cosine is not 13 over 12. Minus 5 over 13 divided by 12 over 13. The 13's cancel and we get minus 5 over 12. And so now from here, you're free to not do any more fraction work. So cotangent, you can just flip tangent. It's minus 12 over 5. Cosecant, you can flip sine. It's minus 13 over 5. Okay. And secant, we already had from the start. So if you want to see how would you work these out in more detail, go back to the previous problem where I write what they are in terms of sine, cosine, tangent. And that's how you do one like that. New problem. So Marco would like to estimate how tall a building is. And so the way he's going to do this is he's going to walk 50 feet away, and then he's going to estimate the angle of elevation from him to the building. And so when he does that, he gets roughly 40 degrees as his estimate. And so now we want to see how tall is the building. Here it's asking us round to 2 decimal places. So here, if I have my building, here it is. It's very tall. And then here's Marco's path from the building. And the angle of elevation is 40 degrees. So this one is definitely not drawn to scale. Well, that's okay. So this is 40 degrees. And then because we know that he walked 50 feet away, we can write that down. This is 50. And what are we looking for? We want to know the height of the building. We want to know this h. So now we think of trig in terms of triangles. We're going to use that instead. Here, h, this is the opposite side of this triangle. This 50 is the adjacent side of the triangle. And so what we set up is, if we have the opposite and the adjacent, then we can use tangent. I can say the tangent of 40 degrees, I know what the angle is equal to the opposite, which is h, over 50. So then h is 50 times the tangent of 40 degrees. So we need to put this into a calculator. And the biggest thing that you might mess up, the biggest thing that you might have problems with is make sure your calculator is in degree mode. So I plug that in, and I get roughly, h is roughly 41.95 feet. And here's where I like to do a little bit of a sanity check. Like, does this answer make sense? So 45 degrees, or if a triangle had a 45 pair like that, where two angles were 45 degrees, this opposite and this adjacent would be the same size as each other, same length. 40 degrees is a little bit less than that, but the numbers should be close. So that's me just like looking at that number and saying, okay, yeah, that does make some sense there. It does seem reasonable. Number 7. An airplane flies in a straight line with an angle of 20 degrees from the ground. And that's at a speed of 215 miles per hour. So the question is, how fast is it ascending? So let's think about that. Let's ponder that in a second. But let's draw what we have. So we have our plane. And it starts on the ground. And then it flies, but it flies at an angle. So this is 20 degrees, we were told. And it flies at a speed of 215 miles per hour. And so the question is, how fast is it ascending? Or in other words, how fast is it climbing into the sky? If I was just in a jetpack next to the plane, how fast would I have to be lifting up into the air to keep pace with it that way? And so this is something, if you're going to take physics or engineering, this is something you want to have down pat. It's just going to make your life so much easier, because we want to break things into their components, vertical and horizontal components, all the time. And what we're doing here is we're just saying, what's the vertical speed of the plane? So I want to figure that out. So what is the, I'll call it VH for vertical. You can call it anything you want, X, Y. Maybe we'll just call it Vy, because it's in the y-axis, V for velocity. And so what do? Well, I have this 20 degrees. I have this opposite side here. and I have the hypotenuse. So if I have the hypotenuse and the opposite side, then that is a sine. I'm thinking SOHCAHTOA. So what I can do is I can say sine of 20 degrees is equal to the opposite, which is Vy, over the hypotenuse, which is 215. So my speed in the vertical direction is 215 sine of 20. And one more time, I pop that into a calculator. And I get roughly 73.53 miles per hour. And again, a little bit of a, does this answer make sense kind of thing. So 20 degrees isn't really that steep of an angle, right? So it makes sense that it shouldn't be ascending that fast compared to its actual speed. And so this 73.53, yeah, that seems pretty reasonable. It seems like a reasonable speed, but that's how fast it's going up in the air. Number 8. So this gives us a function f of x equals minus 3 cosine of 4 times x minus pi minus 2. So this has got a little bit of everything in it, and it asks us to find the amplitude, period, and phase shift to start. After that, it asks us to find the equation for the midline. We're actually going to cheat and find that after instead. And then we want to graph 2 periods of the function. So let's start with amplitude, phase shift, and period. So first, let's just have it down here so we can look at it together. Cosine 4 x minus pi minus 2. And so if we go back, the kind of standard form is a cosine b x minus h plus k. That tells us everything about the formula function. So the amplitude is always just equal to, you take the absolute value of a, so whatever's in front of your sine or cosine, that's the absolute value of minus 3, or in other words, our amplitude's just 3. So remember, amplitude is always a positive number, but that's easy to fix. If it was to be negative, just make it positive. So the amplitude is 3. The period, for sine and cosine, the period is 2 pi divided by b. If it wasn't positive, then just make it positive. So that's what we're going to do here. So this is 2 pi divided by b, in this case is 4. So we have pi divided by 2. This is our period. And now find the phase shift. So when the function is factored like this, where you have the 4 on the outside, then you can just take the number right there, that minus pi, you can take the h equals h is pi. On the exam, if we gave you one like this, we would give it to you factored like this. This is the form we've been dealing with. But if you see other study tools or maybe other books, maybe even other classes, you might have to solve for that sometimes. If it's not factored like that already, then you need to factor it to be able to figure out that phase shift. And just to be sure, because there's h's and b's, this is the h. Looked a little bit like a b. So that answers part A. B asks us to find the equation for the midline. We're actually going to skip that for a second. So we're going to come back to that, because we're going to get the midline pretty naturally when we do part C. So what are we going to do? we start with our little chart. Uh-oh. So now I have the grid lines here, so I have to make things line up nicely. So we get x, and then I don't know why it's doing that. Minus 3 cosine 4 x minus pi. There's a lot of stuff going on there. Minus 2. All right, so there's everything set up for us. Now I think I'm going to give all my points 2 squares just so I'm not trying to squeeze stuff in too much. And so the way that we always start this is we start at pi. This is the phase shift. Here I'm going to call the period P. And the way that I do this is I figure out what P over 4 is. So I always take the period and divide that by 4. Always. And get pi over 8. And so what I do is I keep adding this to pi. So I say plus pi over 8. That would be 9 pi over 8 plus pi over 8 would be 10 pi over 8. If we simplified that, we would get 5 pi over 4. Add another pi over 8. We're back to 5 pi over 4 is 10 pi over 8. Plus another one is 11 pi over 8. And then we do one more. And we get 12 pi over 8 is the same thing as 3 pi over 2. So now we're going to plug all of this in. All right, so let's go. We plug in pi. We plug in pi right here. We get pi minus pi is 0 times 4 is 0. So cosine of 0 is 1 times minus 3 gives us minus 3. Put all that together, we get minus 5. Because this block here is minus 3. And then the minus 2 at the end drags it down by another 2. We put in 9 pi over 8. When you plug that in here, you're going to get pi over 8 times 4 is pi over 2. Cosine of pi over 2 is 0. Times minus 3 is still 0. So then we get minus 2. Move on to 5 pi over 4. Plug that in here. And again, you could put this in a calculator or use the unit circle. You'll have both on the exam. So I'm just going through it through my head real quick. 5 pi over 4 minus pi is pi over 4 for that blue part. Times 4 gives you pi. Cosine of pi is minus 1. Times minus 3 is a plus 3. Times minus 1 is 1. We go back to this blue box with 11 pi over 8. So we get 11 pi over 8 minus pi is 3 pi over 8. Times 4 is 3 pi over 2. Cosine of 3 pi over 2 is 0 again. So we repeat minus 2. And then we could sanity check it, but we do go back to minus 5 at 3 pi over 2. And so now what we do is it said graph 2 full periods. So I'm going to skimp out a little bit. And not draw the entire graph. I know that I'm mostly below. I'm also going to cheat and draw a horizontal line with the tablet. While I'm there, I might as well do a vertical line too. And so these are just going to be ones. And let's say this is going to be pi. That would make this 2 pi. And these blue ticks would be like pi over 2's. And I think we actually have enough space just between pi and 2 pi. Why is that? Because 1 period is pi over 2. And so actually a whole period occurs between pi and 3 pi over 2. How do I get from, I always start right here at my phase shift. So here this is -5. And then how do I know when to go 1 period away? Well, here we did it just from the chart. It's 3 pi over 2. So let's plug in those things first. And so here the way I've drawn it with my spacing, I get a really thin cosine. It's really skinny. It's also decently tall. And now I want to repeat it. How do I know where to end it? So I'm going to take 3 pi over 2, and I'm going to add 1 period to that. I'm going to add 1 period. And that's going to tell me where I'm going to end. So if you like formulas, that's what we're doing. I think it's easier to not think of it as a formula way. Just think about it as we're literally moving a period away. So just add them. So that puts us at 2 pi. And so we're just going to repeat this picture again. And so here that satisfies where it asks us to graph 2 periods. There they are. This first one is like the natural one. The one we got just from doing this little chart. And then we could just copy it over and over. Okay, so here you can see mine was a little bit fatter the second time around. But we have the idea, right? So now we can actually go back. What is the equation? That's an important word. What is the equation of the midline? And so the midline would be, very creatively, the line that falls in the middle. And we said in class, your midline is always the middle number if you do it with this chart. So that's another plus to doing it with the chart, is the equation for the midline is it's a horizontal line. So it should be y equals, and in this case it's -2. It's that middle number. So we went back and did B, because it's easier once we have that chart done. We don't have to go out of our way to look for it. It's just going to pop out when we're doing work that we were already going to do anyway. Okay. And so while we're here, though, I want to say one more thing. So one last kind of thing I could ask you on a problem like this. So we're introducing a surprise part D. Find the, or maybe a better way to write it is, locate a minimum and a maximum. Okay. And so if I want to find a maximum, that's always like one of these biggest points. So here's a maximum at, you know what? I don't want to figure that one out. So let's use the one we already have, which is 9 pi over 8, comma 1. So there's a max at 9 pi over 8, comma 1. I want the whole point if I say this. If I say maximum value, I just want the y value. But if I say find a maximum on the graph or label a maximum on the graph, I want the whole point. And so similarly, a minimum is This one we found over here, the 5 pi over 4, comma, all right. This was 5 pi over 4. I didn't read the table right. Sorry. Normally I would restart the video, but I'm way too far in to do that now. And this is already late enough. Sorry. So this was 5 pi over 4. This is why we always go back and check, make sure. Because now we go to this minimum. That was one of the minus 5. So actually, let's just use our starting point. Our pi, comma, minus 5. Pi minus 5. Okay. And so can you use other points here? Like if you gave me, this would be 3 pi over 2. Could you give me that point? And the answer to that is yes, you could. Same thing, if you wanted to figure out what this x value was here, you could give me that point up there as well. I just want a max. I don't care about a specific one. Number 10. So we skipped 9 because it works very, very similar to 8. And so that's one where you might want to practice on your own, use Desmos to see if you're getting the right sketch or not. And so we're going to skip straight to 10 just so I can actually get this out in a reasonable time. So let f of x be minus 5 times tangent of 2x. And so the question is, what is the period and phase shift of f of x? And where are the asymptotes? Okay. So here we accidentally kept the grid paper, but that's okay. F of x equals minus 5 times tangent of 2x. And so the first thing said, what's the period? So the period, we have a tangent of b x minus h plus k. That's our formula, or that's our standard transformations. For tangent, the period is pi, not 2 pi. So you start with pi divided by b is, here in this case, pi divided by 2, we just get a pi over 2. What's the phase shift? Phase shift. So in this case, I look up here, and there's nothing being added or subtracted from the x. So in that case, our phase shift is h, which is 0. One thing I kind of want to highlight is it should make sense that our period got cut in half because we're multiplying everything by 2. And so since we're shrinking everything by a factor of 2, then it seems pretty reasonable that our period gets cut in half. So I just kind of want to be thinking about that as we move on to the next question, like what's going on there? Now, where are the asymptotes of f of x? So how do we find asymptotes? Well, we take what's exactly in this purple rectangle here. So whoop, 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 here we go. That sound effect was 100% necessary to make the problem work. I take what's inside of that tangent. I always set it equal to pi over 2 plus pi k. Always set it equal to that when I'm finding asymptotes for tangent. Now I divide everything by the 2 that's in front of that x. I'm getting x by itself. And so x is equal to now pi divided by, pi over 2 divided by 2 is pi over 4, plus pi over 2k. And so here's where all the asymptotes are. Any x that looks like this, where k is an integer. Okay, so if I plug in any like whole number value of k, positive or negative, and I solve that for x, then there's gonna be a vertical asymptote there. If you remember from class, you might be able to save yourself some work. If you're finding the asymptotes anyway, the number that is in front of the k is always going to be the same as the period. Okay, so that's how you do one like number 10. One more. Let g of x be 3 tangent of, and then we have a whole bunch of stuff going on the inside there. So 3 tangent of x minus pi over 3 plus 1. And so now once again, what is the period and phase shift? What are the asymptotes? So here I want to find the period. I could solve for the asymptotes first, grab the period along the way. But having two ways to do something's not bad. So here for the period, I take the b value, that's whatever I'm multiplying x by, or here the x minus 3. Well, I look here and there's just shadows. There's nothing in there, which means there's secretly a 1 there, like a little ninja. So if you don't see a number multiplying by x, then it's just 1. So the period is, tangent is pi divided by b. So in this case, this is pi divided by 1 equals pi. So the period remains unchanged. Now let's look at the pi over 3. So that's going to be a horizontal shift. It's going to be a phase shift. And so intuitively, before we even start on asymptotes, that should move those two. But here the phase shift is this h, which is pi over 3. If it's minus, then your phase shift is positive. If for whatever reason we had like a plus pi over 3 in there, then our phase shift would have been negative. You always flip the sign because the formula for transformations has minus h in it. So h is equal to 3. Or sorry, h is pi over 3. That gives us the phase shift. And so now we need to find asymptotes. And so I always, to find the asymptotes of tangent, take the inside function, and I set that to be equal to pi over 3 is pi over 2 plus pi k. It's always pi over 2 plus pi k on the right when you're finding asymptotes of tangent. It's nice, stable, there for you. Always that thing. Now we're going to add pi over 3 to both sides. So x is equal to pi over 3, pi over 2, plus pi over 3, plus pi k. Let's get a common denominator for this. I'm going to need a little more space. So my hope is you're watching this and you're already knowing how to find a common denominator, or even better, that you already have. But in case not, I take this denominator, multiply by it over itself on the other fraction, repeat over here with this fraction. I get 2 divided by 2 plus pi k. And we get x equals 3 pi over 6 plus 2 pi over 6 plus pi k. X is 5 pi over 6 plus pi k. And that's our final answer there. 5 pi over 6 plus pi k. So we've just moved over a slight bit. And here that was all done by the phase shift. So instead of our asymptote starting at pi over 2 and then showing up every period of pi, they start at 5 pi over 6 and then repeat every period of pi. And that's how to do one like number 11.